You push a box with mass m equals 10 kilograms up a 30-degree incline at a constant velocity. The displacement of the box along the incline is 2 meters. The kinetic friction coefficient is 0.2. What is the work done by the pushing force, the friction force, the normal force, and gravity? What is the net force on the box? So over here is a free body diagram of the box. It's displaced 2 meters, that's the change in x. It has the pushing force, the downward force of gravity, the normal force, and the coefficient of friction, or the frictional force. And then we've set y to be the direction perpendicular to the plane of the incline, and x to be parallel to the incline. And this is at a 30-degree angle. So first, we should probably set this equation, since it's in kind of a dynamic equilibrium. It's moving at a constant velocity, so there's no acceleration. So we can write our first equation, which is this force, the pushing force, minus the frictional force. And then there's one more thing we have to add, which is the force acting parallel to the incline done by gravity. And this is derived from here, where the force perpendicular is times the cosine of the angle, and the direction parallel is times the sine. And this can be done using alternate interior angles to prove these two congruent. And then we can just use basic trigonometry to decompose the gravity vector. And then using this, we get minus mg sine theta. And then this is because this is also pulling it back down along with the force of friction. Since it's moving up, it has friction, and the gravity force that is parallel to the incline is pulling it back down as well. And then now this is equal to the mass times the acceleration. Now, we already said it's in constant velocity, so the acceleration is equal to 0. So then we can just generalize this to force minus the frictional force minus the part of gravity that is parallel to the incline is equal to 0. Acceleration is 0, so this whole right-hand side of the equation is also 0. Now, along this y-axis, or the one perpendicular to the incline, you can write a similar problem, except this we're going to have to use the other part of the decomposed gravity vector. So the normal force is pointing up, and the gravitational force is pointing down. Again, we have to use the component that is perpendicular to the incline, because that's what we set up in our coordinate system. The y direction is perpendicular to the incline. Minus mg times the cosine of theta. That's perpendicular, that's the one pulling in towards the incline. And again, this is equal to 0, since there is no acceleration at all. And then, now, we can rearrange this to get that the normal force is equal to mass times the gravity times the cosine of theta. The gravity is no longer negative because we manipulated this equation to move it to the right side. And now we have the normal force. And we also know that the frictional force is equal to the coefficient of friction times the normal force. Now we can just substitute this equation in for the normal force. So we can get that the force of friction is equal to the coefficient of friction times the mass, the gravity, and the cosine of the angle, cosine of theta. And then now we can substitute this back into the original equation. So I'm going to make some room real quick by erasing everything here. And then, now that we have this, we will just simply substitute this back into the first equation right here, where we see minus the force of friction. So then we get that the force minus the coefficient of kinetic friction times the mass times the gravity times the cosine of theta minus mg sine theta equals 0. This is once we substitute the frictional force into there. And then from there we can factor mg out. So force is equal to mass times the gravity times the sine of theta plus the coefficient of kinetic friction. It's not a really good drawing. Coefficient of kinetic friction times the cosine of theta. And now basically all that we did is we moved everything to the right hand equation, so these all become positive. We factor out the mg, and then we're just basically left with this. And then this will just allow us to solve for the work by the pushing force. So let's get rid of everything else here, so we don't need all of this anymore. And get rid of that as well. Then we're left with this equation for the force. I'm going to rewrite it up here. Now, if you remember, work is a force over a certain displacement. So you are applying a force over a certain distance. So you can simply write that the work done by the pushing force is equal to the force of the pushing force times the displacement done by the pushing force. So the work is the force times the displacement. So then we can just simply write that the work of the pushing force is equal to this, which is the force, times the displacement. Now that we have everything, we can substitute everything back in. We know that the mass of the box is 10 kilograms. Know that the gravity is 9.8. And then now, sine of 30, because the incline is at a 30-degree angle, plus the coefficient of kinetic friction. It's getting a little bit squishy here. Times the cosine of that angle, 30. And then times the displacement, which is 2 meters. And sorry that this got a bit squishy, but this is just plugging all of your variables back into these equations. So you have mass, 10 kilograms, gravity, 9.8, and then sine of the angle of the incline, 30 degrees, plus the coefficient of kinetic friction, which is 0.2, times the cosine of that same angle, so 30 degrees again, and then times the displacement, which is 2 meters. Now, if you solve all of this, you should get that the work done by the pushing force is equal to 132 joules, or about 132 joules. It's really close. Okay, so let's rewrite that. we have calculated that the work done by the pushing force is 132 joules. And that solves the first part of the problem. Now, we need to solve, we can quickly solve for the normal force first. So, we know that work done at an angle, we can decompose that into its resultant vectors. And then work is the force times the displacement. And then the force we're looking at is only the force parallel to the displacement. A force that is perpendicular to the displacement does no work, since it's not displacing it in the perpendicular direction. So with that, you can just simply write that the work done by the normal force, simply just the normal force, it's this part right here, and then we're going to have to times it by the cosine of 90 degrees. Since it's acting at a 90-degree angle, and we need the part that is parallel to the incline at that 90-degree angle. And then we're going to times in the displacement, which is 2 meters. Now, we don't even need to solve this, since the cosine of 90 degrees is just 0. So the whole thing, it just simply evaluates to 0. So then the work done by the normal force is equal to 0. And now the work done by normal force is almost always equal to 0, since it is perpendicular to the direction of the displacement, and therefore does no work on the object. Now we can calculate the work done by friction. Now, the work done by friction is simply equal to the negative of the friction force. This is because it's acting opposite to the pushing force, and we set the pushing force to be positive in the positive x direction. So this should be in the negative x direction. And then we're going to multiply that with the displacement, since all work is a force times the displacement. And then if you remember before, we solve that the force of friction is equal to the coefficient of kinetic friction times the mg cosine theta. This was what we solved for it in the beginning of the video. Now we just plug this back in, so we get that the work done by friction is equal to minus the coefficient of kinetic friction, mg cosine theta, and then times the change in x. Now we just simply plug everything back in. So the work done by friction is equal to minus 0.2, coefficient of kinetic friction, times the mass of 10 kilograms, times the gravity of 9.8, times the cosine of 30 degrees, and then finally times the displacement, which is just 2 meters. Now, if you solve everything, you can round this over to minus 34 joules. And so the friction force does minus 34 joules of work on the system. And this simply means that it's minus 34 joules in the direction opposite to the pushing force, which we set as our positive x in our reference system. So I'm going to rewrite this up there. I'm going to get rid of all of this. And the work done by friction to about minus 34 joules to the left, basically. And then now we have another part. We still need to solve for the work done by gravity. So the work done by gravity is basically the force of gravity times the displacement. So the work done by gravity is simply the force of gravity acting on it. So minus mg sine theta. And we're only counting this parallel component because the perpendicular is really just the normal force acting on it. And then you just need to multiply this by the displacement. Force times displacement equals work. And then now again we can plug everything in. The work done by gravity is minus the mass is 10 kilograms times the gravity of 9.8 times the sine of 30 degrees and then times the displacement of 2 meters. And now this, if you simplify everything, the work done by gravity is minus 98 joules. And again, this is also in the same direction as the friction, and so it's acting opposite of the pushing force. It's pulling the box back down, it's opposing your push. So then, let me rewrite this up here. The work done by gravity is equal to minus 98 joules. Alright, so now we have solved for all of the work done by all of these forces here. So now we have to figure out the net force on the box. So the net force, or really the net work, is just the summation of all of this. So the net work is equal to the work done by the pushing force, plus the work done by the normal force, plus the work done by the friction force, plus the work done by gravity. Now if you just plug everything in, 32 plus 0, minus 34 minus 98. And then this just simplifies to 0. So the net work done, the net work done on the box is actually just 0 joules. And then this makes sense because it is going up at a constant velocity. And so the change in its kinetic energy is 0, since it still has the same mass and the same velocity. And the kinetic equation is 1/2 mv squared, and none of those variables have been changed. And then by the work energy theorem, work is equal to the change in kinetic energy. And there's no change in kinetic energy, so the net work is equal to 0 joules. And that is how you solve this problem.